Alright, so I'm going to record this really quick before I go to bed because I do not want to be up for 24 hours again. I've been doing that way too much. 336 hours this week. Okay, whatever. But question 1. Given an orthogonal basis B, U1, U2, U3, U4 for R4, where U1 equals this, U2, blah, 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 let x equal that. Find the coordinate vector of x relative to B. So the first thing we want to do here is we're going to want to find the coefficients of our scalars. Right, imagine this as x being a span of u1, u2, u3, u4, some linear combination. That's basically what we're going to want to find. So we can do that two ways. I would recommend the second one, but the first one involves setting up a matrix. Right, so you're going to store your u1, u2, u3, u4 along the columns, as you can see over here. Let me just get my pen out. Yeah, so right here. Then we're going to put, since we want to solve for the solution of x, we're going to put that on the right side. Right, so once we do that, we're going to set up the matrix. That's u1, u2, u3, u4, x. Right. The next thing we want to do is we're going to want to RREF because we're going to want to solve for the pivots. Right. Because what we're going to end up finding is we're going to end up finding C1, C2, C3, C4. Those are going to be our scalars. And from our scalars, we can form the coordinate vector of x relative to the basis B, orthogonal basis. Right. So I did that. I RREF'd. I got a C1 here, C2, C3, C4. So I wrote that out. Therefore, x is equal to this scalar here for C1, U1, C2, U2, C3, U3, C4, U4. And remember, if you're not sure how to store coordinate vectors, you can go look at tutorial 3, but I just briefly wrote it here. Basically, we want to store the coefficients in order, right, with respect to the vector count, right? So C1's going to go first, C2, C3, C4. Polynomials, you'll do constants, first degree, second degree, third degree. But it actually doesn't really matter. Like, you can define it however you want. Right, just so long as you follow your own definition, that'll work, right? But if you're not too familiar, I covered that more in tutorial 3 that you can go back to. Right, now the second way I'm going to say is just much easier, much faster. REFing like you can just, like a 7x7 matrix or whatever, if you get that, that's a mess. I would never want to do that. But yeah, so if you have an orthogonal basis, where the vectors are of the same dimension, or R4 for the vector we want to solve, we can actually use the orthogonal coefficient theorem, right? So what that involves, just more generally, is just imagine that we have like Ci, that's equal to x, some vector that we want, times ui dot ui. Right, so we're going to do that for every single u vector relative to x. So after we do that, we see we have, well, we want C1, C2, C3, C4, right? That's how many vectors we have. So after we do that, we're going to get the coefficients. We're going to notice that it's going to match the matrix down in the bottom left. So that's good. Sometimes this won't work. I believe the case is if you get a coefficient that's a 0, that results in x not being equal to the linear combination. And in that case, I believe it's because it's linearly dependent. There are a few cases where it'll break down, but yeah, linearly dependent. So if that ends up happening, just make sure that you use the orthogonal coefficient theorem like correctly. You can use it under a condition where it won't work. Similar to the Grant-Schmidt process. That would fail if it's linearly dependent. Orthogonal coefficient theorem should be, if it's not even a span of the original set. Yeah, there you go. If it's not a span. So just make sure you check that. But yeah, that gives us our coefficients. What's B? Write x as the sum of two vectors, one in W equals span, and the other in the complement of W. All right, so this one got a few people. I understand that. Basically, you can just imagine that, well, we have W. We're defining here it to be the span of U1, U2, U3. What is the definition of the span? Or how do we get something from the definition? Well, the definition is like any scalar of the first, second, third. We add them together as linear combinations. So actually take that fact over here. Right, W equals the span of this, well, that goes to this, right? We also notice that the complement, since we have a orthogonal basis B, U1, U2, U3, U4, where W is the span of U1, U2, U3, that means the orthogonal, the complement of W is going to be the vector we did not include, which is going to be U4. Right, so using that fact, we get U4. Similar to the above, when we have the W equals the span, we can take that out to be some scalar combination of that, linear combination. Since it's alone, it's just going to be the scalar itself. Right, so now we have these two pieces here. It wants us to write it as two vectors, though. Well, so what we can do is we have w is equal to this combination. We can just take that combination and just combine it all into one vector. That'll give us 1. And the second one will give us 2. So we do that. X equals C1, U1, C2, C3, blah, blah, blah. We're going to combine all these pieces, and we get the vector down here. This is going to be our W. This will be our WT, our complement. Right, so therefore, that is going to be the complement. Right. Okay, so we go on to the next one. What's number 2? I need to drink water. Okay, given y is equal to this vector, u1 is equal to that, and u2 is equal to that, find the closest points to y in the subspace w spanned by u1 and u2. I just wrote a note down here as well. If it asks you for the shortest distance, you're going to want to take the length of z, right? This comes from our decomposition of y into 2 vectors, y hat and z. If it's shortest distance, find the length, the norm of our z. If it's the closest point, we're going to want our y hat, right? So just make sure you keep track of that. Anyways, our y hat is just going to be equal to the projection of, and what do we want to find? Find the closest point to y in the subspace. So we're going to want to do that relative to y, or with y, relative to w. Very important. So we're just going to take the normal projection formula there, right? We're going to have our basic vector inputting in here. That's going to go to spot 1, spot 2. Every other vectors are just going to follow this formula of ui, 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 ui. And the next one, next one, next one. All right, so you're going to do this for everything. After we do that, we're going to write it out. We're going to get this giant mess over here. This piece is going to be your scalar, right? Your coefficient. This is going to be the vector. You don't always have to take the scalar or coefficient and put it in. Just make sure you read the question. If it asks for that, then you would do that, but that can save you some time. So just make sure you have to do that. Just save you some time. Like we get this piece right here. Since we specifically want the closest point, we don't want the combination. If it asks for the combination, we can just leave it at that. But we want the closest point, so well, let's just simplify that to make it easier to look at, right? So we combine these two, and we get this piece over here. But yeah, that's the closest point. If it wants shortest distance, make sure you take the norm or the length of z. Oh jeez. What's this? Let y equal blah, u1, u2, da 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 da. Verify that u1, u2, the set is an orthonormal basis for w. So we're going to look at all of our pieces. The first piece is we're going to want it to be orthogonal. So the definition of that is we take all of the vector pairs within our set, make sure that the dot product goes to 0. Right, so we did that. u1 dot u2, that indeed goes to 0, so therefore it's orthogonal. The next piece, though, is it orthonormal? Right, the definition of that is such that the length of all of our vectors in our set, or the norm, right, goes to 1. So when we take the norm or the length, I also wrote how you do that here. Right, like remember if you're doing the norm, that's going to go to the square root of first element, second, dot, 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 third. Just square them all and add them all together. Right. I think I did that for first question too. Let me see. Yeah, I just remember like if you're doing the dot product, first element times second, right, first, second, dot, 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 and just add them all together. Okay. But yeah, so we see that it's orthogonal, the length in the norm is 1, therefore it's an orthonormal basis for w. B is find the orthogonal projection, right? So we can just take our vectors, we already checked that they're orthogonal, right? Part A, u1 dot u2 goes to 0. So an orthogonal projection is just going to be those vectors with respect to y, and we have our y vector at the top and over here, 3. Right. Since it's projection y with respect to w, of y onto w. Yeah, you can say that way as well. We're just going to take, once again, y in the first slot, second slot here, ui, dot, 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 dot. After you do that, you're going to find the combination such that it adds up to 2, 4, 5. That's the same as before. C, let u equal vector in the first column, second column, compute U transpose U and U transpose. Is this an orthogonal matrix? Okay, so when it says U1, U2, right, we're going to store those vectors as columns. Right? If it were U1 over U2, that would be rows, but in this case, we're doing it as columns. Right? That implies that the transpose is going to go to, well, U1, U2. So you're going to need those two pieces. I wrote out what they're equal to. Right? So if you're taking the transpose, you're going to take this, you're going to store it as the first row. This, you're going to do the second row, right? So imagine first column, first row, second column, second row, so on, so on, so on. So we get that. We do U transpose U, matrix multiplication. If you're not familiar with that, you can just look at the previous tutorials or the notes, right? But yeah, we see it's equal to the identity matrix 2. However, UUT is equal to something else, right? It's a 3 times 3 matrix, 2 times 2 matrix. In this case, it's asking, is it an orthogonal matrix? Well, since UUT does not equal UTU, which is equal to the identity matrix, U is not an orthogonal matrix, right? Usually what we want to find, we want it such that we have UUT is equal to UTU is equal to the identity matrix given some dimension, right? That's what we want, such that it's orthogonal. Since that is not the case, we're going to say, nope, it is not an orthogonal matrix. Next is compute UUT, right? So we can take our piece up here. We computed that over here. Just simply bring that down. Multiply it by our y vector. The very fun thing is that we see that we once again get 2, 4, 5. Right? So we see UUT, y is equal to the projection y with respect to w, or onto w. I like to say with respect, but... Alright, what's this? Vectors x1, x2, x3 are 4. Let w equal the span of x1, x2, x3. Justify that it is a basis. Right, so we already have that as a span, right? The next thing we want is linearly independence. So we can just set up our matrix, right? So once we set it up, we take our x1, x2, x3, put them in the columns, set that equal to 0. That just makes it much easier to deal with. You don't necessarily have to set it equal to 0, but that's just more work. I would not do that. Alternatively, you can consider the dimension and the number of free variables with respect to the set or your space. If we have a free variable over the dimension, right, you got to make sure. Too many would make it dependent. Right? I think I've already showed that in our previous tutorial as well, but yeah, that's just something you can also do. Right? But yeah, so once we RREF this, we find that we have, well, the identity matrix with an extra row. That's important because we have 3 columns, right? C1, C2, C3. This row is not going to be considered C4, guy, right? It's only with the column. So we have C1, C2, C3. Those are all equal to 0. Well, that's great, right? Because that means that's linearly independent. So then we can say that, therefore, since W is a span containing only linear independent vectors, x1, x2, x3, they form a basis for W. I have seen some people take, 0 equals 0 to mean it's a free variable. Remember, we're looking at the columns, right? Those are where our variables are. So that's why I just mentioned it earlier. All right, B. Use the Grand-Schmidt process to produce an orthogonal basis for W. Right? So that's just going to involve the normal formula of, V1 goes to X1, V2 goes to X2 minus X2 dot V1 over V1, 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 right? And then so on, so on, so on. V3 equals X3 minus X3. You can just imagine it as like the projection over and over again. X3 minus the projection with V1 minus projection of X3 with V2 minus projection of X3 with V3, blah, 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 blah. Well, only in the case where it's Xn minus 1, right? That's where you're going to go up for V. Right, so anyway, we use that. After we use that, we're going to get all of our orthogonal vectors. You can check that as well, right? 'Cause sometimes you might mess up the multiplication or addition. We know this process is guaranteed to provide an orthogonal basis such that it follows that it is not linearly dependent, right? If it is linearly dependent, I believe you get 0 for one of them, right? Yeah. Yes, you can check, right? V1, V2, V1, V3, V2, V3. They're all equal to 0, so they're all orthogonal. So therefore, v1, v2, v3 form an orthogonal basis for W. Let's see. Find an orthonormal basis of W. Okay, so that's just going to be, basically, we're going to normalize all of our vectors. Right, since we want that the length of all of them is going to be equal to 1, such that it's normalized. Right, want that equal to 1. We can just simply take the vector and then divide it by its current norm to get to 1. Right, it's basically just like, it's just A over A. Right, that's going to give us 1. So we do that for all of our vectors, and we see that we're going to get 1 over the square root of 20 over and over again. It's very interesting. Oh, because we also see, look, we have 3, 3, 3, 3, 1, 1, 1, 3, 3, 1, 3, 1, 1, 3. Since the norm involves square roots with squares, right, that means that all of these are going to be positive, so they're all going to be the same thing. So if you do notice that, if you notice that this goes to this goes to this, well, they're all going to have the same length or norm, right? I saw some people calculate it differently for each one, but you can use the fact that it's squares within, and it's all the same coefficients to mean that it's going to be the same result. Just look out for that. But yeah, so we see, we normalize it, we have the orthogonal from above, therefore it's orthonormal. So we say, therefore the set forms an orthonormal basis for W, of W. Oh, I need to cough. Hold on. Alright, anyways, find the orthogonal projection of B onto the column space of A. Right, so we see the column space of A is just going to be the span, the first column, second column. We can imagine that's x1, x2. Since it wants an orthogonal projection, we're going to want to check if it's orthogonal currently. We see that it's not, right? We get the dot product is equal to 15, which is not equal to 0. So, without like changing the vectors, we can just apply the Gram-Schmidt process to them to find what would make them orthogonal within the column space. Right. So take the first column, that's x1. Take the second one, that's x2. This is guaranteed to give us orthogonal vectors once again, such that it follows the conditions where it's not dependent. Yeah, so we get that. After doing that, we get this result over here. Once again, you can check if this is orthogonal, just to see if you messed up. After checking, we see that it is, right? The dot product 0. So we're good to go. Now we want B hat, which is equal to the projection of B onto the column space of A. So we're going to use the projection formula once again. Just B here, VI, 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 so on, so on, so on. Add them together, and you're going to get your result here, right? Just projections over and over and over again. Go to the next one. Find a least square solution of AX equals B. So there's two ways to do this. I just like to do, you multiply the A transpose on both sides, right? That's equivalent. You can do that. Make sure you do it on the left, right? You want to get it such that we can multiply these results and then combine them, simply here. We multiply it onto the right side of the x, that's just going to be a mess. Yeah, like look at that. What is that? Ew. Anyway, so you find the transpose. Once again, first column goes first row, second column, second row. Multiply both sides, so we have it over here as well. Just some matrix multiplication to get this result down here. And then this result over here, right? First element, second element, second, third, first, second, third, so on, so on, so on. And you do that for the second row as well, in case you forgot how to multiply. But yeah, so we get this. In this case, we can just set up the solution, right? So we have x. So we can imagine that this goes to x1, x2 is equal to this side, right? Left side goes to right side. RREF to find the pivots for our solutions. First pivot, second pivot, that's going to be x1, x2. Therefore, we can say overall, x is just going to be equal to 4, -1, right? So that is it for that.